So, we are continuing our series Basics of University Math, and uh, we arrived within the part 4. We were dealing with the part 4, currently maps. We arrived in interrelationships between image and pre-image, and we wanted to look at, let's call it part 2 of the bigger part maps, part 2. And next up, we'd like to take a look at the following objects. Of course, again, for f being a map from some set x to some set y, right? We are already familiar with that. And since we apply preimage here, and a and y, and here we apply the image, so b element x, right? All right, and we'd like to take a look at such objects. And of course, the natural question that we are wondering about is that equal A by chance? Or is that equal B? Or is there at least a subset relation in play? Let's take a look at that. All right. Well, let's just imagine our first one of those subset relationships, at least in the first case, should be obvious, right? Because like if we take an element, right, this is a set, so I can apply the image to that, and we have that we apply f to some element of this pre-image, right? I consider element y this set, and we know just by definition of this set that applying f to an element of the pre-image of a set just catapults this element into the set, so this subset relationship is obvious, right? Right, but what is about the other one? So this is checked. What is about the other one? Isn't A always a subset of this thing? And we will write it properly, of course, in a second. But first, let's discuss it just orally. Well, let's think about it a little. And if we take an A and we take this thing, nope. Indeed, that's not true, because let's take just something like that. And imagine we take a map like this, right? And this is no problem, right? For each input, we have an output, so that this is left alone. And this is indeed the domain of our map. So y consists of those 3, x consists of those 2. That this is left alone is no problem. It doesn't contradict the definition of the map, so everything is fine, right? But if we consider even here the whole pre-image of y, then that is those 2 points, and you can of course take a special set, specify that somehow, okay? And this y is actually this whole thing, right? But f of f minus 1 of y is of course only this, because we can't get more out of it, because we can only map to this 2. So let's do it like that. Here we're free. and we are only interested in those two. But anyway, it's just a scheme, right? So this is not always true. Okay, and what about this one? Well, again, one should be obvious. Which one? Well, let's say we, okay. Yes, this one in this direction. Because you see, if we take an element in here, then this is just pre-image. Oh, I mean, like, this is any element in this set is an element such that any element X in this set, so an element in X, we take pre-image of that set. Pre-images are always subsets of the domain, right? So we take any element X in here, and this is, and the pre-image is defined as the set of all such elements X, such that f of X is in f of B. And then the question would be if this x is if f of x is in f of b, would that then be true that x is already in b if we consider this direction, right? We consider this direction, that is, we are trying to establish that for each x in here, this is indeed in B, and indeed that's not the case, not generally not the case. We'll see it in a second. So this is probably not this direction. If one is obvious, then that's certainly not this direction, because for each x theoretically, well, if f of x is indeed in f of b, it need not be that x is indeed in b, so probably not this one, but we'll discuss it in a second, so you'll see it too. Okay, but let's take x in b, right? Let's take x in b and go to there and consider whether it is true that f of x is in f of b, because that is exactly the definition of this set. If we look at how this set is defined, it is pre-image of this set. And how is pre-image defined? Well, it's exactly those elements of x that by mapping them by f land in this set, right? That is the definition of pre-image. But any element of x when mapped by f lands in this set. This is just the definition of this set. So this is certainly true. All right, that was this one this time, and that is true. And another one is indeed not true, because we could just consider something. We always went to the top, so let's go to the bottom maybe. We just consider as, and this is of course if that is mapped, and that is x, and that is, let's say, y. And then we consider just this b, right? To establish that the other direction is not true, we consider this b. So b is x, and we have f of x is just equal y itself, but f of minus y. No, not that. We consider only that, okay, give it names like 1, 2, and 3. So we consider that f of 2 is indeed equal the whole set y, and I should be careful. Of course, we conflate that if it is just single element, and we often write something like this, but actually I'm interested in the image, so let's do it this probably for once. We have that this is already y, because we have only one element, so 2 is certainly mapped to 3, so f of the 2 certainly contains 3, and certainly 3 is contained in f of 2, because that is just the definition of f of 2. So this set is equal to a set containing 3, right? Just look at that, pause for a little and look at that to see that. And now f of minus 1 of y, which is same as f minus 1 of f of 2. Well, what's that? That is all elements that map to this, and this is x, and 2 is not equal x because x actually includes both. So the other one is wrong. Let's just do out of it remark. Mark for a map, because it's too easy to be a lemma, right? For a map f a lemma or a theorem, let alone theorem, map x y f for any a subset of y that okay, that's this one. So that is true. f minus 1 of a subset of a is really called, right? But in general, not necessarily. Right, not necessarily the other direction. So the other direction might fail to be true. All right. And for any b subset of x that b subset of f minus 1 f of b, but in general, no. And in general, no is just a shortcut for in general, no, not necessarily. Because in general actually already includes that it is just not necessarily not an absolute not. But in general, no. Okay, now that's kind of disappointing, right? That we don't have that. We would actually like to have that. It's really natural. It seems to be very natural. Like, ah, like, how could that be wrong? But in general, for general maps, seems to be wrong, right? I mean, how can that be wrong? I mean, we have f minus 1, kind of would be nice if it would be true. And here same, just would be nice, right? Right, would be nice if those that are actually not true now are actually true. Were actually true. And for some kinds of maps, for some especially nice kinds of maps, those both turn out to be true. But let's consider them in due order. What went wrong here, for example? Let's tackle first this issue. We had that without problem for any map. But the reverse kind of didn't work because, well, we can see what went wrong here. It was kind of this more going in, I mean, more going in sense of being mapped to free than we actually got out of what we put into it. So we put into it only true and we managed to get free, but it turns out we could have taken more to get same free, meaning by mapping. We could have taken more elements that actually give free, right? That was the problem, that we have taken only some of elements that give free, which is legitimate. This is a subset of X, right? But the problem was there were actually more, and we got those more when we applied that, when we got back and looked at all elements that gave this free, right? And in general, it is just a general set. We could construct more general examples, where it is just a general set, right? A general set, I mean, in a concrete example, but not just a set containing one element. Okay, so it kind of seems that the problem was that multiple elements could be mapped to same element, because this is what ruined it. If there was no such one, then it would be just mapping forth and back. And if you imagine a situation with more elements, like, but you imagine like they all go, there might be some that are left over, but you all go nicely, then you just go back just the same from the image to the pre-image, and what you put in that you get out, because each element only has one arrow leading to it, right? We would just trace it back, no problem, as long as we consider such a set. Right? But here, this one was problematic because we haven't actually counted for it by taking this set too. So what map or what property should a map have that for all choices of sets wouldn't actually face this problem that we haven't accounted for additional elements, giving elements in the picture of the elements that we have accounted for. So what map would alleviate that problem of things being mapped to same things, but being able not to be accounted for all sets, subsets in the domain? What map would do that? And to resolve this issue, we could have an especially nice type of maps, and those are called injective maps. Injectivity. A map, and we will require exactly this property. A map X to Y is called injective if it is true that all X, Y, okay, that's bad, of course. Let's call it Y1, Y2. All Y1, Y2, and 1. Actually, X1, X2. Let's formulate it like that. X1, X2, element Y, and this is just elements. It's not big letters, it's small letters. And Y, we have that f of X1, f of X2 implies that X1 equals X2. And what does it mean? Well, whenever it is true that for some element it turned out that this element is mapped by f to same thing. So exactly the problem we were facing there, and now we are alleviating this problem on the very level of each element, right? So when it turns out, then already the element was the same element to begin with. And of course, it's a more self-suggestive thing to formulate this like contraposition. This is of course equivalent to, and I'm not writing equivalent, I'm just writing that as equivalent as alternative formulation, right? Whenever the elements were unequal, yeah, images will be unequal. But as definition, I wanted to state it like this because you should get used to mathematical formulations, and this mathematical formulation is, so to speak, more structurally. I don't know how to describe it. More structurally involved, so to speak. Here you see a typical principle of mathematical thinking and work. And this is more natural, more immediate, right? So exactly this problem should be eliminated here, that we had elements that we could have not accounted for when we took images because they were elements mapping to same elements via f, which we haven't taken a look at and haven't taken them into account by building our image of a set. So we haven't taken them into the set, right? And we were allowed to choose such sets because we were allowed to choose any subsets of the domain, and we wanted that property of that interplay of f minus one, I mean of preimage and preimage, that this property holds actually for any subset. So yeah, we wanted that. And now let's see. Our guess is that for such maps it works, right? Our guess is that for such maps, indeed, the following holds. Indeed, that is true if I'm writing theorem that for such maps we already have that f minus 1 f of b theorem. Let f be let f be a map injective. Shortcut is this. We write that in short fashion like this. Then for any b subset x, we have indeed equality. So not just one direction of the set equality holds, but both directions. Right, of subset relation, but subset relation both direction gives equality. We have indeed that. So we have really nice thing, right? All right. Okay, so one direction we have already discussed just without writing it down, but let's just do it. That is this one for any map. And you remember, I won't write it down explicitly anymore because we are already a little bit mature to understand that without being specified explicitly, that we just show both subset relationships in that direction and in the direction. And for any map, we have just seen in particular for this one, because let x element be f of x is of course element f of b, that's just the definition. And then again the definition of f minus 1 f of b, x element is 1 f of b. If you don't see it directly, and that is completely normal, then just pause and think about it a little, how the definition applied, what the definitions were, what they are applied to exactly what object, specify that in your mind and you'll see it. Okay. The other way around, that is, we have a subset relationship. Let x element f minus 1 f of b. And that is now for our injective map. We have seen it doesn't work for general maps. So injectivity has to come in somewhere. Then f of x element f of b, just by definition of a preimage, right? And here the magic of injectivity is worked. Then f of x, just by definition of the set, equal to, because if it is an element of f of b, then f of x is same mathematical object, or more precisely, same element as an element f of b for some b in b, because that being element means it is a mathematical object that satisfies that it has the form f of b for some b in x, because that is the definition of the set, right? Of x. And again, this step is not necessarily trivial. It's just uh, it makes sense, yes, but it is just not an exact logical step. This is connected to how we discussed what an element of a set means. This is mathematical object, right? This mathematical object is in the set, and that means that this mathematical object is of the form by definition of the set. This mathematical object, even though written here in that form, but being element of this set means that it is also of the form f of b. Just by definition of this set, any mathematical object in it is it. So in particular, this object. By definition of this set, it is f of b for some b in b, right? This is the definition of a set, right? For some b, element b. Now f was injective, and yes, as you can see, I kind of increased the pace because, well, we are already on a level where I can afford it, right? X equal b follows. Right, just definition of injectivity applied directly. We had f of x equal f of b, then x equal b follows, and hence since that was some b, element b, x is equal exactly as b, and hence x equal b, element b, because we took this b in b. And that finishes it. So if it was too fast for you, just contemplate about it, think about all definitions precisely, and you'll see that it works. It is pretty normal and common that in a mathematical lecture you have to read proofs another time for yourself, that you have to establish for yourself what the concepts exactly mean, and only then you read the proof and understand that. So that you don't understand that immediately, completely normal. The video gives you the benefit that you can immediately pause and immediately contemplate it. Right. In a real lecture, you don't have this benefit, of course. Okay, well, now, of course, we would need to fix it also, or to find the fix for this situation. Well, what was the problem here? You recall, this was always the no problem, right? But this here was problematic. So when something was left alone without the thing being mapped to, then we had a problem. Why exactly was that the problem? Well, we had another direction, right? And now we went from a set to what mapped to the set. Here could be more elements or something, right? But we went from this set to what maps to this set. And of course, we could have chosen this set arbitrary, and so we always could have chosen, if the map allows it, that is, if the map is defined like that, that there are some elements in the target space left over, you could always choose such a set where such elements are inside, right? And then we go back to all elements that map to this, and then this element is already left alone. So for this, we won't find an element that maps to it. And then when we apply this, of course, this element won't be covered because we couldn't cover it. It was already chosen that way that it couldn't be covered. So what map would avoid this issue? Of course, a map that, this is then also in X, a map that maps to everything. And other than that, it need not be ejective, it could be anything, but it has to map to everything. And then we suppose, well, probably then it works. And it did. This is called surjective. Definition. Surjectivity. A map f x y is called surjective. And here you see also directly that a map really is considered as a mapping from a set to a set. So to name those sets is important. It is included in the definition of this map F. So you can't just say a map is F. No, a map is from set to set. You specify the sets, and only that defines the map, this triple. Map set set. It's called surjective, and here you see that in this definition directly. If f of x, that is the image of x, is actually y. Well, f of x is of course subset of y because that is where we map to, right? This is just exactly all the images of elements in x, and they are all in y, so this direction is immediate. But we also now want to have this direction, that is every element of y is actually of this form. And this is called surjectivity. Right. Or you could rewrite it, of course, just from what I have just told you, follows that that is the same. Okay, let's write it like we know to write it for all y element y. Yes, it's just what I told you. It's just that this is equivalent. That just results from the understanding what that actually means, right? For y element y, there exists x element x, such that f of x is actually y. So there exists an x that maps to y. Right, and now we'd like to have the other theorem for a surjective map. F from x to y, have f minus y, what, or maybe the other way around. I constantly forget it. Like, I could realize that immediately, but I would have to realize it actually every time new f of f minus 1a. I mean, I would have this step of realizing it, even if it is immediate. Even if the step is immediate, I would have to look it up in my mind, how it works. F of f minus 1a. F of f minus 1a. And this is now equality. So if you are mixing it up, well, just don't think about it. Just think about how that worked, why it failed in one way, in another way, in one case, in another case, and then you come up with what holds when. That's normal to fail remembering that what was the direction for what kind of map and so on. Right. One thing is immediate for, of course, for a subset Y, arbitrary. So arbitrarily chosen subset. And one thing was immediate, that was namely, well, if we choose such a subset of Y and we go back and we go forth, of course we will end up a subset of this A. So that simply holds for general map. But let's recapitulate that. Let Y and, well, actually X minus 1 f of f minus 1 of A. Okay, so we now consider the one subset relation. And here that held for general maps, right? But let's recapitulate that. As I said, let one element of f of f minus 1 of A. Yeah. Well, what does it mean? It means y is equal f of x for x and f minus 1 of A. But then just because this x is element f minus 1 of A, we have that f of x is element of A, right? But f of x was y, right? Just the definition. X was element of this. That means f of x is element of A. But that was y and so on. So let's proves this direction. And now get to the other direction. Of course, here surjectivity should come into play. Otherwise, it shouldn't work, because for general maps it didn't work as we realized. And we show us exactly the absence of surjectivity. So let y element A and well, when we just have to find such element in here, such that f of this element is y, right? And in here is x and x with f of x equal y, and of course x is element f minus 1 of a, because f of x is equal y and y is in a. So x is an element for which f of x is actually in a. So x is element of f minus 1 of a, and y equal to f of x, and having that as element f minus 1. Okay, and that finishes with proof. Alright, so we have that for those nice maps. We have indeed, respectively, that and that for different kinds of maps. But of course, it would be nice to have both for the same map. And well, nothing prevents us from having that. Definition, and we also have special nice maps, which we are about to define. We are about to define a new kind of maps, not necessarily new, but maps having both properties. A map f from x to y is called bijective. If, and in definitions we don't write if not if, but of course it's always non-leaf definitions. If we only consider the meaning, but the customary is just if, because it's obvious that it is if or if. If it is surjective and injective, both at once. Alright, let's pause for a second and think about what a bijective map is. Picture we know no elements are left without an element that goes to it, right? So no elements are left. To each element there is an arrow, right? Maybe there are two arrows, but two arrows are impossible, right? Because it would be bijective. So only one goes to one. Again, two arrows are impossible. To each there is some map to it. So, and of course, that arrow could also go here instead of here, but then really instead of. This would go, here instead of here. This would go here instead of here. This would go same, but what I mean, no elements are left off, and to each element there is only one arrow. This is bijectivity, and it kind of seems like by bijectivity we could go back. But let's first address another thing. It seems like really bijective means that we could actually, in this case, separate those sets into pairs, taking one element from here and taking the element that is mapped to it, and taking another element and taking an element that's mapped to it, taking another element, and that way we would obtain all the elements from the two sets, the domain and the target space, exactly having in no pairs same element in any position, right? Alright, this is a picture. And indeed, there's a theorem that postulates exactly that. Theorem F is bijective. F call this set F, right? As a union, right? You recall that F could have been described in terms of a set, right? Alright, here's a union. Pairs X, Y, X, element X. Such that for x1, x2, element X, x1, y equal x2, y, x1 equal x2. Right, and we recall this is just, and this is just what we have from the definition of f, right? This is just that this is set f of x. From the definition of f plus mutation f of x for the y that is appointed to x. Right? This is just that. And such that oh, let's do it like that. Y that is with x in pair, right? We have to do that, otherwise it's not clear what y is. And for each y and y, we have y is equal to x for an x element x. So in total, that just means exactly that we can separate that in such pairs where a pair is given by the relationship given by the mapping, right? So a mapping gives exactly a separation in such pairs, right? This is just stated here in terms of this union with certain properties, right? And the proof is just obvious, right? If we have f like this, and of course it is a subset of this, because, well, we could just say, this is yx, we define it as yx and this element of y, and that's the only requirement, right? Okay, where, of course, we should have stated that x element of y, yx element x. But this is not really a theorem, it's more like, I don't know, more like some kind of rewriting what bijectivity is. So I mean, there's nothing to prove really. we just define yx like that, so that is a subset of that, right? Because we just have sets that unite over same pairs, right? Because yx is just chosen like that, so we can define it like that, right? So that is a subset of that. And of course, the other way around is just that. Oh, actually, if we have defined it like that, then it is already equality. We just define yx as f of x. So proof. Okay, let's write something for it, even though it's trivial. Define yx equal f of x. Right, we have set like that, and then it's completely same sets because in each pair the element that is in the pair here is already x always, and this is already same element if we have defined it like that, right? So we have chosen yx to be that, and then that's same, right? And now we have to prove what? Well, that it is bijective if and only if that is true. Well, let's suppose that f is bijective. Well, what does it mean? It is surjective and injective. And well, if it is already surjective, then for each y element y, we have x element x such that y is equal to f of x, right? And then this y is equal to y of x, and hence um, we have that for an x element in x, right? Alright, then we have this thing, and well, we have said that this is just x1, f of x1, this is x2, f of x2, and hence that is just x1 equal x2 for these pairs if we have taken them from here, right? Here, x2, right? This is just this, nothing special. Right, that was for bijectivity. Now we have to show bijectivity. We have that, well, clearly we think it's surjective. Clearly we think it's surjective because, well, if we have that for an x in x, then f of x is equal y of x is equal y, right? So I mean, take any y element y, and it is equal y of x for x element x, but this y of x was chosen to be f of x, so we already have that. We already have that y is equal to x from x element x, right? Because y of x was chosen to be f of x, and now they exists. Now they exist such y of x. We have chosen to be f of x, right? Well, I think I should formulate that more carefully because probably it's hardly understandable what I'm talking about.
I was a little bit lazy here, as you can see, because it's just such a trivial thing, but let's do it completely differently. You see, not being lazy is a little bit difficult when you can allow yourself some freedom after you can already assume that your students have achieved certain level or should have achieved certain level. You should have, because we are already near the end of the introductory course on your basics, right? So when the introductory course, respectively course on your basics, theorem, well, from x to y is bijective. If y is equal to a union summand x, x such that f, oh well, let's just remember that that is actually f, by definition of the map. Such that, so it's if and only if, and that all goes in, right? And here it continues, right? And such that that is equal to this union over x limit x over some yx, the charges elements of y, right? And such that for, and if I'm not saying anything, of course it means for any such choice, so for all such. So next to element x f because it's pairs, right? Have x1 have x1 comma x2 x1 comma x2 and simultaneously. Okay, you need to have that everything at which y and y exists such x, because we have already that. Right? So y can be decomposed in such yx, the whole y, because that's set equality, right? To, and so such that this actually provides us x by x, meaning that's exactly what I stated above. Right, that is F. That's remapping. And that mimic provides us such division pairs, which goes on until the sets are completely separated together in such pairs. Right? Don't mix it up with Cartesian product, because Cartesian product will be each with each, if with each, and not each with a choice. So, and not it. Okay, that's what I wanted to say. Okay, proof. So let F be bijective. If it is even to width, then we have to prove that, right? We prove the both implications. F be bijective, and F is surjective. X, Y. And let Yx equal f of x. And then this condition is satisfied because, well, because this is equal to y, right, by surjectivity. So this, if we replace it by f of x, then this is exactly the whole image, and then we are done here, right? Okay, and this is also satisfied, right? And we only need that condition. And furthermore, so x have bijectivity of f. Right, this is just defined as that, as we said. And we have bijectivity x1 equals x2. So this direction of implication is finished. Now we prove the other direction. Now let the conditions be satisfied. And show f is bijective. Well, from obtain for x and min x. Okay, let me do it slow. Why is that? Well, that's simple. You see, if we assume that this equality holds, then each such object is in this, but the pairs are only equal when both elements in pairs are equal, right? And the equality could not hold of the pairs if the axis would be different, because if the axis would be different, then the pairs couldn't be equal because the first elements are not equal. So if that isn't that, then this must be exactly such a pair with same x. And this I just looked at for each separate x. And for x, f of x equal yx, because the pairs have to be equal that way, and then also the second elements have to be equal. Right. Since equal y, obtain via this f of x is equal y, and f is surjective, and via the condition f of x1, f of x2. Now we have that, right? And that is a big X, big Y, of course. Since we have that, let's call it star. That is star. That is also by star. And that by this, right? We are assuming that whenever we have that, we have this kind of injectivity where those are actually assumed yet at that point to be just y, just some y's in correspondence to x, not necessarily f of, but together with all those conditions, and we have already established that, we have that y x1 equal x2, x1 equal x2, and we have started by this, obtained that. This shows f injective. So, alright, we have that, and again, if it was a little bit too fast, and just contemplate everything, I know it might be a lot, it might be too fast a jump in abstraction, yes, but you have to get used to it. There's no way, can't make it easy the whole time. Right, and this just means, well, that exactly this is given for f. So, conclusion, I will remark, hence bijectivity is also called one-to-one correspondence. For each y and y, there is, so there exists, and there is exactly one. Matrix mapped to it. Projectivity of f and in quantors for y and y, and quantifiers, I mean, there is exactly one. Recall exactly one. Excellent, X mapped to it. And that means we can build those nice pairs. And that we have shown here, right? Now we actually have last theorem, I think. Another characterization of bijectivity, which is especially useful, but already nothing special for us, because we can see now if it works like that, then it's very self-suggestive that if we can go one direction, then we can no doubt go another direction. And if we take recomposition, like we take recomposition of this direction of map, right? With this direction of map, well, we just arrive where we started, right? We go this direction of map, I land here, and when we take recomposition of the map going in the other direction, we just arrive where we started, right? And the other way around. If we take this map first, and this, we just arrive everywhere where we started, right? So it's very self-suggestive, that theorem. F xy is bijective if the call that's if and only if it exists G, of course yx, we go the other way around, just think of it element wise, such that f G is equal f G, and think about where this map goes. First it goes by G, and it goes by F, so that should be Y, and such that this holds. Let me write it properly. Such that f G, so recall that composition is written like that. We first apply that map, then we apply that map. So hence, if we first apply that map, we have go to here to there, and there to there. So that, and when we arrive, we just went Y, G, Y, right, and that was another point, but now we do F, and we arrive at same Y, so that's just that. And composition does exactly that. Well, go by the map. Go by the map from this point to the point to which it brings it, and which point is at that one. And very important, we need both directions. In some certain cases, one direction suffices. In general, no. We have to prove both directions, and that, of course, for x, for element y, x element x, right? Abstractly written, if there exists like existence of a map, blah blah blah, but what is happening is completely clear, like, right, element wise, and we just define element wise this map, it goes back, right? Just like that, nothing else is happening. The map G is called inverse map of F. Inverse because we kind of invert the action of F, right? And F is called invertible. and bijective. Because of that, is also called invertible. Alright, and now let's prove it. Well, of course, we prove follows our very insightful realization here, right? Let F be bijective. If be bijective, use theorem above. To define G y to x. And how would we define that? Well, just recall our theorem about pair representation and just take how each element in Y is represented like that, and just take G of Yx, G of X. Here we have to show that it is well defined, because theoretically we could have like that this, the same element as this, right? We could have that, and then we could define this map, because if it is different elements, we could have that for elements. I mean, theoretically, if we were not in our situation, but generally wanted to have such definition, and of course, we would have to take care of this giving a proper x, because otherwise the map would not be defined. Because which one do we take if it is the same mathematical object that has both representations with same structure? But in our case, we have that, and hence, so we have that property, right? Recall. And such that for x1, x2, limit x have, whenever those are equal, x1 is also equal to x2. So what we have, G is indeed well defined. Well defined since for x1, x2 have x1 equal x2 by those properties, right? Those yx, the bijectivity gave us the possibility, as we have proved, to represent a set such that all those properties were satisfied, in particular this property, right? The structure goes with this property in case of bijectivity of f, right? So look at it, look at that, alright. And hence, for such an object, if it has two such representations, we have indeed that it is a proper map. and it might be multiple, but then for any such 2x we could just consider respective equalities and it would be same, even if it is many, right? And hence we have that. Alright. Alright, we are actually almost done. Almost done with this course, basics of university math. But let's continue. So we have defined such x as a g, and now we just have to prove both equations of both those equations for the respective elements. Let's do that. That Vg that we define in such way really gives that, and then we are done with the direction. If f is bijective, there is an inverse map, right? And that is well defined, right? Very important thing about it, why it would not be well defined otherwise. In mathematics, such things are very important. Otherwise, you might define an object and it might turn out, if you don't check that you end up with empty set. And if you already have proved some nice properties for objects that you have defined, but you have not checked well defined, and then it turns out those objects don't exist, well, it wouldn't be nice. And people tell a story that it has already happened sometimes. So it wouldn't be nice. Alright, let's check. Let's check. The desired equalities. Let element y and how if relation g of y is equal as you recall f of g of y, just definition of composition, right? And then we have to look as what that is defined. Just f. Okay, we have to f of g of yx from x element x. Just recall that any such y in y is such a thing for an x element x, and since we have that for unique x element x, right? And now that was just what did that map do? We just defined it. It just mapped that to x. So we have f of x. But now recall the properties of what we had above. And that's exactly that. So that's yx. That's equal y. For x and x have. Sorry that I'm writing here and here. It's just that. So here we use the property. Here, right? We use the property that for some x element x, we certainly have that this y, since the element of y is equal to this yx, right? We had that property, and we had that equality, and we had that respective pairs were equal to respective pairs, and hence yx was equal f of x. So let's keep that in mind. And here we now have for an x element x have y equal to yx, hence we have that equality, but now g of yx was just equal x just by definition of g, right? And now we had here f of x, that was now yx, recall that above with equality of pairs, right? We could also look that up in the theorem again, that we had that equality of pairs, like that, because the pairs could only be equal if first elements are equal, and since we are going over all elements x, then they are all different unless they are considering a pair with exactly same x, right? So, and then those are equal, and this was x chosen, so that is that. And this is a unique x as we know, so yx is equal 1, y by choice, and that is what we wanted as that equality, right? Alright, so one equality is proved, as you see, f g y any y is equal y, right? Now let x element x, and have to prove the other equality, and g f of x is equal g of f of x is equal, well, just recall what is f of x. We just had that is g y x, right, and that was defined as x, so that works. So G is a well-defined map that satisfies both equalities. With that direction is proved. If f is bijective, then there is such an inverse map. Alright. Okay, let's say there exists already such a G, then we have to show that f is bijective, right? Alright. Let now there be G satisfying equalities. Now, what would we like to prove? Of course, we'd like to prove that this theorem, that the condition of this theorem here is satisfied, that all those conditions are satisfied, right? Okay, so what do we have to prove? We have to prove that representation of y, we have to prove that equality, and we have to prove that kind of funny injectivity of those elements assigned to it. Okay. Define again, well, do we do? Of course, we just do that, right? And okay, and assume, and pay attention, it is not VG from above. VG from above we defined in case where f was bijective, right? Bijective. And now that case is finished. Here we have shown there exists such a G, and here a new case begins. We just assume that there is such a G. We don't know anything about f yet, but we want to have not anything, we know no inequalities, and we want to have f bijective in this case, right? Okay, define that like that, and show first. Y is equal x element x yx. Assume there is such that there is no x and x. That is the case if not surjective, right? There's no x and such that there is no element x if yx equal y. Alright. Then consider equality. And of course I could have done it without contradiction. You can think how it is very easy, but now I'll do it with contradiction. But then consider equality. Y at est equal y, f of g of y equal y, and have a certain x giving y is equal f of g of y is equal y g of y, and g of y is an element x, of course, because g maps y to something, right? It's just how g is defined. So there is such a g, it satisfies with equality. This is element of that, and then that is that, and that is contradiction. And as I said, we can do it without contradiction. We could just say, well, there is actually which y is such an element of x that it works, and hence our assumption was wrong, that there is y element I such that there is no element x. So, and hence for each y element y, there is x element x with, that's how I write with sometimes. It's like without, but without O. Yeah, with y equal x. And of course, here we just started by an assumption. We got something wrong, and the implications were true. And of course, we use the other part of the definition of implication, and we must have started by something wrong because the implications were true, but we gave something wrong, so the premise must be wrong because from nothing true could have come something wrong by right implications, right? But here we could have immediately seen that actually there is x element x with y equal to yx simply by taking x equal to g of y, right, for the y. And you would have had that immediately, but you see, both structures, you could use them, it is completely valid. That might be a little confusing, you could rewrite it differently, but mathematically it is both completely valid. Alright, that was the first thing. Now we have defined that by definition. Have the other condition x element x right, because we have explicitly defined, and as you have noticed probably, we always define yx to be just f of x, and this is well, I did not have to introduce that at all. I could have talked always about this, but it just seemed to me to be nice to think one time about assignment and another time to think about such pairs in which it is distributed. But of course, since we always actually take that like f of x, well, there's no need for that really. Okay. Okay, by definition that, left to check. Right, so that we have that equivalent identification and that equivalent set of conditions to bijectivity from the theorem above. We have to check y x1, y x2 is equal x1, x2. In other words, the injectivity. But we have f of x1 equal f of x2, which is equal to y x1 to y x2 by our definition. Therefore, and of course, those are elements x1, x2, any two elements of x. We have that g of x1 equal g f of x2, because we are applying to same element, right? It's same mathematical object, we apply to same object g. And also we have that equality that this is just x1 and this is just x2, right? It's just that equality that we have about the composition of g with f, right? And this we had equal mathematical objects, apply same thing, and I use definition of composition, then I use quality that we have, and we obtain that. Okay, that shows all the conditions from the above theorem, where we characterize bijectivity via separation of the two sets in pairs, one by one. It shows all the conditions from the above theorem, and hence f is indeed bijective. And hence f is bijective. Okay. Remark for a map f xy, its inverse g from the theorem that we have just proved. This g is denoted as f minus 1. So that is just notation. It is denoted as f minus 1, but that is defined as g because we had g as an object derived above. And now we define f minus y to be f minus 1 to be that g with that properties. And is bijective. Of course it is bijective because its inverse is f, which you can see immediately from that, and I'm not even stating that its inverse is f. The inverse is like a dual thing. If something is inverse of something, then this something is inverse of it. And so inverse is something is inverse of something. So first thing is inverse of second thing, and then second thing is inverse of first thing. It's just how inverse relationship works. It's not something is off, but it is more like in two directions. Okay, and you can see, of course, immediately that f is inverse of g because the relationship is just symmetric, and this is how it is meant to be. Right? Inverse is, recall that always, inverse is a symmetric relationship. It's not that something is inverse of something, it is somehow symmetric. No, it is always both. That is what inverse is. Relationship of inversity between two maps. Right. Okay. And we have our last definition. a map identity x from x to x, and well, if it is identity, then it just leaves things identical. Identity x equal x for x element x, and I could have written that, of course, also like that. You already used all these notations, you understand what they mean. It's called the identity map. It is of course unique because it is defined by this relationship. Identity map on X, but of course it's important that it is on X. Another set would be another identity, of course. I already know what equality of maps means, so you know that. Okay, and can rewrite university of f x1 g ix has fg and equal identity, also written with small I. It's one time like that, one time like that, it doesn't matter. Only structures matter. So you see that relationship of above is exactly that, right? Identity x, or well, like we introduced just now, minus 1 is our g, so I and f minus 1 is our g, and hence identity x. Okay, with that, I think our course about basics is finished, and next we will do more specific things. So, right. I think next we should take a look at matrices, because it's kind of a prerequisite mathematics arithmetics. I mean, primarily, it's kind of a prerequisite for my course on linear maps basics, and well, it's good to have it on the channel as well. Right. Of course. Basics of university maps. Primary part is finished. Okay, what could we look next? Well, there are a lot of things that we could look at, and they are quite interesting things. Already we can do really interesting stuff, and that's great, isn't it? Next up, Mhm. We'll see what we'll do. I don't know if it will be still part of this course. We'll see. Mhm. I don't have anything on my mind, so I guess from there already starting mathematical calculus. Um, algebra. So yes, I think we should have that. I think from here we will go here. Definition of real numbers. We adapt a top-down approach, etc. Into structures and matrices. Formula guides, variance, nation variance. Maybe determinants, characteristic moments, Hamilton. Yeah, well, explanation theorems for solving linear systems. And I mean mathematical formalism, not just techniques. Yeah, we'll see. I certainly would like this topic very much, because in this topic I really would have to do something. I would really have to think of proofs hard, because I don't know if I did that properly. I would like this topic, but on the other hand, that would be prerequisite for the course. And after we have done that, you actually can already tackle course basics of linear maps, if you wish so. I think you pretty much can. The prerequisites are pretty much matrix calculation, and other than that, just makes that really clear, right? In this course on basics of university maths. Equivalence classes is also a nice topic generally. It's a very powerful tool. And through the year we have, of course, like, well, not necessarily for all the year, but yeah, abstract algebra. Basic algebraic structures. Groups. And so on. Right, alright. There then probably probability theory. And then here we can do something that's really somewhat familiar with by now. Mathematical statistical mechanics. Right. Also from here, of course. Mathematical calculus 2. From there in mathematical calculus 3. Plus some basic back measure theory. And from there, surjective geometry. Enter here. But I don't know if I like that very much. So, of course it's nice, but it's more like from abstract algebra. Enter here. Geometries. It gives a nice setting, but it does not necessarily give hands-on tools. Okay, from the best geometry sense. Okay, I think that's approximately what it will look like. Okay, well, that's more for you, for me than for you, just to know. But you can also have an outlook at what I intend to touch, to cover, depends. I mean, of course, like basic probability theory. New number. That maybe not so basic. Probability theory. New function. It's actually more like this, but okay. Well, we'll see about that. Where we'll get with it. Maybe there is not much basic literature. Basic matrilinear. Basic commutative algebra. Alright, that's what we'll do, but for now, that's it. And that's what we'll do eventually. No exactly goes. Oh, I'm pretty much interested in that topic, because I have not really looked at that, I think. I have not taken a close look at that, I think. So yeah, let's see. Okay.